So we'll see. So today we're going to start talking about the real world. All right, we're going to move away from the cradle, from the classes that we created ourselves, and start using the real thing. And to that end, we are going to start talking about the Java libraries. So many of you, anybody who's taken Java in high school has already seen most of this, but now we're going to start learning about it for everybody who has not done that. So in lecture, so far, the story of the class has been about building data structures. And we've basically given some exemplifications of ideas that are going to be important to us throughout the rest of the semester for the next 10 weeks. So in particular, we in class built a list61b interface, and we also developed an A-list and an S-list class, which were okay, but they didn't do everything efficiently. So for example, what did S-list not do super efficiently? Add last, right? And so we gave you a chance to go and build something even better. You had a double-ended queue, which had a few more operations than a list61b, and in your case, you were able to efficiently support add and remove last using the ArrayDeck and LinkedListDeck implementations. And so in both cases, what we ended up doing is we had an abstract data type, like an idea, right? The thing that the people in the cave believe, and then we had the secret actions of the monks. So I did a version, you did a version. Okay? Now, of course, there's this stuff here, and then there's the real world, which we'll see in a moment. But before we get to that, I will say that in addition to this has been the main story of the class so far. We had a little bit of a sidetrack, which is another nice use of implementation inheritance, which was for comparison. So we saw that with interfaces. Hey, this is actually kind of a bug. You know what? I just realized this is from last year. This should say interface inheritance. Anyway. Curses spring 2016, Josh. Anyway, so two more uses for interfaces that we saw, in addition to capturing this nice story, is it gives us a contract that where we can say, if you are an R-comparable object, you definitely have a compare method. So in this case, we're using interface inheritance to say what your capabilities are. And so you could say that a dog, for example, has the capabilities of comparison. And also gave us a way to get around the fact that in Java, we can't pass functions along inside of we can't hand off functions as arguments to functions. So as a result, we are able to use interface inheritance to basically create objects like, say, character comparators. That's something you did in Project 1C. So that you built a class that can basically act kind of like a function generation function in a way, in the sense that you could pick arbitrary m. Okay? So in other words, we've used interfaces in two ways. First, we've captured this really nice idea of walling off the abstract universe of the people who live, the abstract universe of the people that live in the cave, in the true universe of the monks wiggling around their things in front of the flames, and we also used it as a way to express the capabilities of objects. Okay? So those are two ways you could think about what we've done so far. So this idea of drawing a line between the people in the cave and the monks, we are now going to start seeing what it is that the real world does. So instead of the double-ended queue that we implemented or that we made up just for the purpose of this class and these that you invented, we're going to move on to what Java will do. Okay? Now this notion of this distinction between an abstract data type and an actual implementation is something that we're going to harp on over and over again. And so what I'm going to do is start introducing other abstract data types. So we've seen the double-ended queue in class, and throughout the next half of lecture or so, we're going to see others that you've seen before. Okay? So here's a new one that you may or may not have heard of before, known as a stack. So what is a stack? Well, it's an abstract data type that has two operations, push and pop. And in this case, it's just integers. So for example, this stack currently has the number 4, and if I start pushing things, they're going to go on top of the stack, because it's a stack of things. So if I push the number 6, it appears. If I now push the number 2, it appears. And now, the only other thing I can do with a stack is pop. Okay, what does it mean to pop something off of a stack? Well, in this case, 2 will go away. So it's a lot like a double-ended queue, except it's single-ended, right? So we can only put stuff and take them off of the top. So that's what the stack abstract data type is. Now, there's basically an infinite number of ways that you could implement this thing, but I want you to just consider what you know already. If we were to try and implement this new abstract data type that you may have never seen that has only these two operations, which of these two do you think would be faster? So give it a shot. Think about this on shoutkey.com/rainbow. Okay, we got a vote of 4-1 in the favor of linked list. Someone who thinks array is a better answer. Who's willing to say why? That's the less popular answer, I'll warn you in advance. But why do you think array might be better? Yeah. Well, why is it better? Yeah. Yeah. It's easier to pop and unpop from the end. So what do you mean? How would you pop, for example, with an array-based implementation? So you would do size minus 1. If you did it with a linked list, what would you have to do? You might have to iterate through the entire list. Okay. Why do you not need to iterate through the entire list to pop? Linked list, buddy. Yeah. Well, you were a proponent of linked list. You guys are debating now. So why don't you have to iterate through the whole linked list to get to it, though? Oh, so you're proposing that the pointer will always be to the top. So if you have a top pointer, then you don't have to iterate through. Okay? So what I would argue is if you do the linked list where you keep the pointer to 4, then indeed it will be slow. But if you keep it on 2, it'll actually be okay. You could argue that maybe possibly it's a little more work each time you remove from a linked list. I don't know if it really will be. So the argument that maybe why would an array be slower would be my next question. You have to resize sometimes. Now, is it a meaningful difference? It turns out for a stack, it doesn't actually matter which one you do. It'll pretty much be equally good, so long as you make sure that you're tracking with the linked list the last, or the top. Okay? So as long as you keep a top pointer, they're going to be about the same. But a linked list will have a slight advantage because it will never have to do the resizing operation. Okay? How about another one? No, another one. Here's another abstract data type that you've probably never heard of because I made it up. It's called a grab bag. So in this case, it supports 4 operations. It has insert, which inserts X into the grab bag. And the bag is just a bag, right? It's this bag. It doesn't have any particular order. I just like toss a thing in it. When I do remove, let's put some things in it. Okay. I don't know, these things. I take out some stuff, and then I have this thing, which was already in there. And then I got something back. So that's remove. You get a random thing. And sample means to basically look in the bag and be like, microphone, okay, but not take it out. And size tell me there's some number of things in the bag, okay? So that's an abstract data type. You can use that without even knowing what a linked list or an array is, but let's suppose you tried to implement it. Which one do you think would be a better implementation overall? Just use your intuition. I need my phone. It's in the bag. Dang it. Okay, the room is not quite, but is nearly unanimous. So this time I'll just say array people. Why do you think it'll be faster? So for sample, with an array, you can just pick a random number between 0 and the number of items or however it's stored, and you can go straight there and get the item you want. With a linked list, presumably it'll be a little more complicated because to do sampling, you need to scan through the list. And even if you kept like a random pointer, you still need to keep generating random pointers, which involves necessarily scanning over the list. So there you go. So arrays in this case will probably be, well, in fact, will be a much better solution. You could maybe do something sneaky with a linked list where you also keep an array of all the items, but then you're kind of cheating.